In this series of videos, we're going to be reviewing our basic knowledge of how to read the most important document in chemistry, that being the periodic table of the elements, as well as using the information within the periodic table in order to understand patterns that we call periodic trends that occur when we read from left to right or right to left and top to bottom or bottom to top along the periodic table. This video, however, is simply meant as a review to orient ourselves and know how to read the periodic table correctly, where the beginning and where the end is, and what the names of the most important element families are. So, firstly, how are elements organized in the periodic table? Well, we know from looking at hydrogen, the first element, that hydrogen is element number 1 as indicated by its atomic number. Now, if you remember your atomic structure, you will know that atomic number tells you the number of protons that exist within the element. So hydrogen has 1 proton, making it atomic number 1, and then because of the fact that we read the periodic table the same way that we read English and most other European languages from left to right, we can see that when we go left to right from hydrogen, we get to element number 2, helium, which would have 2 protons, and then we skip down to the next row for element number 3, lithium with 3 protons, element number 4 is beryllium with 4 protons, and so on and so forth. So as we read from left to right, we see that the elements increase in terms of their atomic number, and therefore increase in terms of the number of protons from left to right. Now, there are 2 terms that are used to describe rows and columns of elements. We're going to start with rows, specifically rows where we look at the periodic table horizontally, because this is where we actually get the name periodic from, because each horizontal row of the periodic table is what we call a period. Now, if you remember your knowledge of atomic structure, every time we get to the end of one row and the beginning of the next row, each new period that we add represents an electron shell that we add. For example, if we draw the structure of hydrogen using the Bohr-Rutherford model, hydrogen only has 1 electron, and the maximum number of electrons that can be held in the first shell is 2, meaning that lithium, because of the fact that lithium has 3 electrons, its first electron shell will hold 2 electrons, and then the second electron shell will only hold 1 electron here, but we can see that lithium requires a second shell. So hydrogen and helium, because they are on the first period or the first horizontal row, they would have 1 electron shell, whereas elements from lithium all the way to neon will have 2 electron shells, because the second shell can hold up to 8 electrons in total, which is why we have 1, 2, 3, 4, 5, 6, 7, 8 electrons per row for lithium and sodium. Now, what about columns? What about if we were to read vertically? Well, vertical columns have a much less exciting name, and these are what we call groups of elements. So technically hydrogen is on its own because it kind of has characteristics that are similar to metals and non-metals, but generally is grouped separately. But the elements lithium down to francium comprise one group, beryllium down to radium comprise another group, fluorine down to astatine comprise another group, and so on and so on. Now, what you will find, for example, if we compare hydrogen and lithium, if we look specifically at the outermost electron shell, the shell that is farther away from the nucleus than the inner shells, which is what we call the valence shell, and if we look specifically at the number of valence electrons, hydrogen will have 1, and lithium will also have 1. So a common feature of elements in the same group is that they will always have the same number of valence electrons, and this is easiest to observe when we actually take a look at some of the major element groups or element families. Now, broadly speaking, it's easiest to talk about the elements on the left-hand side of the periodic table, which are our metals, again, predominantly found on the left-hand side, because there are actually many examples of element groups, i.e. elements in the same vertical column, although we refer to these as element families because they all share similar behavior. So if we go from lithium down to francium, these are examples of what we call our alkali metals, and the characteristics that they have is that they all have 1 valence electron, as we've seen with lithium, and for reasons that we'll get into when we talk about chemical reactions, this makes them very, very, very reactive. I'm sure everyone has seen, if not a video, then in person, of sodium or potassium being dropped into water and watched with pride and joy as they explode in a very violent fashion. The next group to the right, yes, indeed, the right of the alkali metals are similar in terms of structure and behavior, and that's why we call these the alkaline earth metals. Instead of having 1 valence electron like the alkali metals, they actually have 2, which makes them slightly less reactive than the alkali metals, but still very, very dangerous stuff. Magnesium in particular, when lit on fire, explodes in a brilliantly bright light, which gives it particular useful application in fireworks displays. That is the source of the light that fireworks give off when they explode, is the burning of tiny pieces of magnesium. Now, in the middle, between the alkali and the alkaline earth metals, are a family of metals that don't make up a single group, but act as the transition point between the alkali and alkaline earth metals and the non-metals, and for that reason why we call these the transition metals. And again, we find these in the middle of the periodic table between the alkali and alkaline earth and the non-metals, and a common feature of many of the transition metals that you don't see outside of the middle is that many of these metals, but not all, are multivalent, meaning that they have multiple charges. Now, if we make our way to the far right-hand side of the periodic table, there are 2 key families, the first of which being the halogens, which include some of the most deadly and poisonous substances on Earth: fluorine, chlorine, bromine, and iodine. And these are the most reactive non-metals, which is why many of them are very, very, very dangerous. And the common characteristic that they share is that they all have 7 valence electrons, which is 1 electron away from having a full valence shell. That brings us to the final family, or the final group of elements that we're going to review, which are what we call the noble gases. So noble gases, unlike the halogens, which are very deadly and because of how reactive they are, noble gases are completely unreactive, meaning that they basically just sit there and take up space because they actually have 8 valence electrons, which gives them a full valence shell, meaning that the noble gases do not gain or lose electrons, which is why they predominantly do not react with anything. In the next videos in this series, we're going to use all of this background information, as well as our knowledge of atomic structure from Science 9 and 10, in order to learn about a few predictable patterns that occur as we read up and down and left and right across the periodic table.